Okay, so we are looking at a titration curve of sodium carbonate, okay, a solution of sodium carbonate, 40 milliliters of sodium carbonate of some unknown solution, titrated with 1.0 molar hydrochloric acid solution. Okay, so this is what we've gotten, and for those that look at this kind of strangely, I did not use a drip counter. We used basically a Logger Pro system where we were just measuring milliliters. We did 1 milliliter at a time, and we got good enough data to make this analysis, and it's a nice quick way to do the titrations and for the kids to see the changes. Okay, yes, I know it's not as precise as a drip counter, but you do get through these quicker, and I can do a bunch of these, okay, next to each other, and they can compare and contrast. So any case, getting to the pH curves, okay, we are going to first look, and the first couple of things that I wanted was I wanted to recognize the equivalence points and the macroing positions, because what I'm asking for is I'm asking for the two Kas. I want the Ka of the acid dissociation constant of the carbonic acid, H2CO3, and I wanted the Ka of the bicarbonate, HCO3. So essentially, we have this carbonic acid, and it's a diprotic acid, and it has two Kas. All right, sometimes they call it a Ka1 and a Ka2. We're going to look for those two and do some analysis, and we did so by dropping, okay, from the burette 1 molar hydrochloric acid, which is a strong acid, and of course the sodium carbonate is going to dissociate into carbonic or carbonate ions, which are weak bases. Okay, this is a basic salt because this negative ion can accept 2 protons. It can pull protons from water. This is a pretty strong base, but we don't typically call it a strong base. It's a weak base generally, and this strong acid will push its protons on it stoichiometrically. Any case, so the questions I'm asking are to validate the initial and final pHs. I'm asking you to figure out the max buffering positions and the equivalence points. So the first thing I do with a curve like this, before I get to the concentration of the unknown solution, is I'm going to look at my curve and identify some important pieces. All right, so any case, I'm going to see here, and I'm going to make a general estimation that my equivalence point is somewhere in this vicinity here. So I'm between 19 and 20. So I'm going to make my equivalence point 19 and a half. Okay, and it's a guesstimation. Okay, so I'm going to say 19 and a half. So 19.5 milliliters of the acid that was dropped. This bottom line is volume of hydrochloric acid that was dropped from the burette. Okay, so this is the volume. So I needed 19.5 milliliters to titrate to neutralize the first part of this titration. Now, what actually happened in this position of 19 and a half? What happened right here? And it's important you start writing the predominant reactions. Well, we had, let's change some colors, we had CO3 negative 2 accepting a proton from the acid to make the bicarb ion. Okay, and we were making that happen. So at this point here, we had 100% CO3 negative 2, and at this point here, we have 0% CO3 negative 2. Okay, now we have 0% of the conjugate base, HCO3 negative, and at this point, the equivalent point, we have 100%, I'll just put that right here, 100% of the conjugate base. Okay, no problem there. Now, that must mean that if it took 19.5 milliliters to titrate completely neutralize, okay, this carbonate ion, then shouldn't it make sense that the halfway between 19.5 and 0 would be the amount it takes to halfway neutralize it? So half of 19.5 is what? 19.25 or 9.25? So 9.25 somewhere along this here would be, okay, my max buffering position. So this is my max buffer position. I call it max buffer position because we're going to have 50% of my base produced, and we're going to have 50% of my my conjugate acid produced, and I have 50% of my base still there. Okay, now why? Because this volume had a certain number of moles of protons that produced the halfway point, or had enough moles of protons just for half of the available carbonate ions. I know that this is an equivalence point. There's that, tangential line going down. Okay, so this has to be the place where the moles of carbonate were halfway titrated. And you should know from me or from other teachers that when you titrate a base halfway or titrate an acid halfway or even part of the way, you create a buffer because you're creating some amount of carbonate ion and some amount of HCl3. Now what's nice with this position is we can actually start solving for one of my Kas. But before I do that, I want to know what my concentration is to verify this pH here. So I want to figure out what the concentration is of my unknown sodium carbonate solution. Now, I know some people want to go to MV equals MV, but with these graphs, you don't have to. Didn't we just figure it out? It takes 19.5 milliliters. It takes 19.5 milliliters of hydrochloric acid, to completely neutralize my base. Okay, let's go backwards here. I don't know what just happened, and move it over. Okay, so it takes 19.5 milliliters. Let's just get this away of my acid, I should say, if I didn't say that right, of my HCl to neutralize this amount here. So what I'm going to do is I'm going to use this point to find the concentration of my base, of my original base solution. So I'm going to take 1 liter. I want to make 1 liter out of this. I'm going to divide by 1,000 milliliters. And the reason why I'm doing this is I want to use the molarity of the acid that I know. For every 1 liter, there was 1.0 moles, because the molarity was 1 molar, right? So I'm getting rid of my liters, my milliliters, and now I have moles of HCl. All I did here, guys, was figure out the moles of HCl that was dropped at this equivalence point. Okay. Now, interesting enough, you may not need this, but I like to keep things very clear. So what I'm going to do is I know that for every 1 H plus, okay, oops, let me just do it the other way. I know that for every 1 HCl, all right, we're dealing with HCl, 1 HCl, there's 1 H plus. And I do that just to keep myself straight in terms of, this could have been an acid that was diprotic, okay, but it was a monoprotic acid. Now the next thing, so I get rid of my hydrochloric acid, and now I have moles of proton, okay. Now, the next thing I'm going to do is that, again, you may not need to do this, and with time constraints on an AP, you certainly don't do that, but just to make this straight, for every 1 H plus, there was 1 carbonate ion, -2. There it goes. All right, now this gives me moles of carbonate ions, doesn't it? I don't need to completely titrate everything to answer this question. And what I'm going to do is I'm going to divide by, okay, the original concentration that was in my beaker, right, because we're adding the HCl, okay, to the CO3 ion. So the original concentration was 40, so I'm just going to divide by 0.040 liters. And what I get is moles over liters. This is going to give me, okay, 0.49, okay, molar concentration of my original solution. Look at that. I didn't have to completely neutralize, okay, CO3, okay. All I had to do was neutralize it once. Now you may say, Mr. Grodsky, what if I did the second equivalence point? Because doesn't CO3 negative 2 gain 2 protons? Absolutely. So wouldn't it need twice the volume? So if this is 19.5, this should be twice the volume to get to this point. Okay, well if you're using twice the volume, all right, you notice you're going to have twice the number of moles that's being added, and because every one CO3 negative 2, okay, requires 2 H's, you'd have to take those moles and divide it by 2 to do that. Okay, so case in point, let me put this next to each other if you don't see it. If I took the total volume, all right, which is, let's say, 39 milliliters, notice I'm just doubling it. That's what this value would be here, okay, of HCl. And I do the same thing. 1 liter over 1,000 milliliters. Milliliters cancel. I'm just converting to moles. So 1.0 moles for every 1 liter. Liters go, and I got moles of HCl. I know that for every 1 H plus, for every 1 HCl, there's 1 H plus. And look what I'm going to do here. For every 1 CO3 negative 2, it requires 2 H pluses. Okay? 2 H pluses. And then I would divide by 1 over 0.040, and I would get the same answer. So if I'm going to use a second equivalence point, it's double the volume, double the moles, but then I'm dividing by, okay, 2 here, because for every one of these, well, I just cut to the chase and just used one of them. Now, if you notice something, we should be at, okay, we should be at 39 for the second equivalence point, because those values in between stay pretty constant. It takes 9.5 for every position. So 9.5 would get us to the max buffering, and 9.5 would get us to 39. But you notice it's less than that. It's less than 38. Why isn't this line hitting 39? Well, why isn't it coming out and doing this? And there's a reason behind that, which is unique to this type of titration. Most other titrations, the exact distance will be there always once you have halfway. The reason why this one doesn't quite work out is because any point that we make H2CO3, if you noticed, you're going to produce CO2 in water. So that disappears. So the H2 doesn't sit around to the end here. The H2CO3 decomposes because it is an unstable molecule. That's why you saw bubbling happening along this area. Every time you saw bubbles appear along this curve, okay, that means you were driving this off to CO2 and water. So there was less base there at the end. That's why you see that this line should be extended, but that's why it's been shortened. So it is more accurate to use the first one. And again, this is unique to this titration. We were losing the H2CO3. That's why, okay, less acid was needed to be added than would be normally if this was a scenario where the compound being made at the end of the titration was there. Since if you don't follow me, look what happens here. If this is 0% CO3 negative 2, and this is 100% HCO3, well then as we titrate the HCO3, and I can find as we titrate along this line, okay, we get to the second buffer position, and this represents a place where you have 0% HCO3, because what's happening in this reaction, okay, the predominant reaction here between this position Okay, remember we had the predominant reaction for this part is we have HCO3 negative gaining a proton from the strong acid and becoming H2CO3. So once this was made, it didn't stick around. A lot of it became CO2 and water. Okay, so it's part of the reason why that there's a little change there. But in any case, okay, you have supposedly 100% H2CO3 here, and you guessed it, our max buffering position, which should be somewhere 9.25 greater. So again, trying to do my math in my head here. So 19.5 and you add 9 is 28, 28.8 something. So the max buffering position, if I'm not mistaken, is somewhere along this point here. And that's, of course, where you have what? You halfway titrated this base, so therefore you have 50% of the HCO3 negative, and 50%. And, of course, at this position you have 50% of the conjugate acid that was made, H2CO3. Okay? And that's how those percentages play out. All right, now, so the most predominant part, and let's keep going here. Once we get past the second reaction, the reaction that occurs in this region, okay, which is, I would say, after this point here. So all this region right here, the predominant reaction is just what? HCl plus water, making hydroniums. Okay, and the Cl negative if you want. Okay, or you can just say, you know, H plus, or the proton, plus water, making the hydronium ion, at the net ion if you want to do it that way. But that's what's happening here. And you need that to understand that to validate the final pH. The final pH is, hey, everything's been neutralized up to this point. How do I get this final pH validated? I'm asking my students, whatever pH you have here, see if it makes sense. Well, if you noticed, you added 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 milliliters of HCl after the equivalence point. Well, everything has been what? Titrated and neutralized at this position, so you don't have anything but just extra protons. So figure out the moles from 13 milliliters, just like we did in our other concentrations, other titrations we've done. So figure out the total moles of 13 milliliters, which is very simple. You know that's a 1.0 molar solution, and you know that 13 mils is 0.013. Molarity is equal to moles over liters. So if you do it this way, you get 0.013 times 1. Okay, don't know why I put that in a calculator, but I get, of course, 0.013 moles. Great, I have my moles. Now what do I do with that? Well, I need a molarity. Well, what's the total concentration? Volume. Well, we added 13 milliliters, but what's the total volume here? At this point, you have 50 milliliters of acid that was added, but you had original what? 40 milliliters. So you've got 90 milliliters of total volume in that position. So that's 0.090. I have to be in liters to get my molarity. This one I have to do in my head, 0.1 of my calculator. Divide by 0.090, and I get a molarity to be 0.1444. That's my concentration of my H plus. Of course, to get my pH, I do a negative log of that. So negative log of my answer, and I get I got 0.84. So my pH was 0.84, and that's what it should be theoretically. Now we're getting something here. This is a pH of 1, 1.2. So it's not that far away from reality. So 0.84 is typically, now of course this depends on calibration and any other problems you may have had in measuring, if I didn't measure out the 40 milliliters of HCl exactly and those things. But that's certainly a close enough approximation. So that's how you find the final pH, just like you found the finals in the other ones. Once you're past the equivalent point, it's just the extra acid base that you added over the total volume. Now the initial pH, okay, the initial pH I want you to validate. Well, you just have carbonate ion. My friends in chemistry, what is the pH of a carbonate ion? Well, I guess we're going to need to have its Kb. Okay, and with its Kb, we have to do an equilibrium problem. Knowing that you started out with a certain number of moles of sodium carbonate, we can do this. Now, of course, to do this problem, we're going to need the concentration of the carbonate ion. So I can't do this yet until I actually find out the Kb. Okay, we did find out the concentration is 0.49 molar, so I can figure out my moles, but it still won't happen until I get my Kb. So what you're going to have to do at this point, okay, is deal with these max buffering positions. Now, for those that still not quite getting it, the max buffer position at halfway to equivalence is very important for us graphically because of the Henderson-Hasselbalch formula. pH equals the pKa, okay, plus the log of your conjugate base over your conjugate acid. So we want to find the pK. We want to find a pKa, which will, by doing 10 to the negative x, we can get the Ka out. Now, you certainly can find the pKb's here. My question in this lab was to find the 2 Kas. Now, we could use the pOH to find the pK, but since these values are in pH, I'm going to keep it in this formula. Okay. Now, so let's go find the Kas of each, and then we can do the inverse. We can find the Kb's to solve for that. So let's go find what this would be. All right. So the pH here, at the max buffering position. Okay. Well, I don't have the data in front of me, but I'm going to guess about 9.8 is my pH, and you could find that from your graph and look at your data and do that. So I got 9.8 is my pH. I'm going to solve for my pKa, and I know that the log of, at max buffering position, I have equal the amounts of each. That's why it's the halfway point. Half of the moles of the acid was added. It made the same amount of conjugate acid as base, so these are equal. And you should know the log of these equal numbers, which will be 1, is 0. So this becomes, hey, my pH equals my pKa. And to find my Ka, okay, all I do is do what? 10 to the negative 9.8 to find my value. So I do my calculator, I do my 10 to the x, second function if you've got a TI-84, second function 10 to the x, and I do 10 to the negative 9.8 to take my pKa and make it into a Ka, and this Ka for the bicarb ion, okay, I'm just going to put that in parentheses, HCl3, is equal to 1.58 times 10 to the negative 10, okay, for my data here. All right, the second one's done the same way. Okay, max buffering position means that the pH equals the pKa. Now, this could be the Ka of something else, but sincerely, this, okay, value, we'll say is, I don't know, 6.2, somewhere around there. So my pK is equal to 6.2 to 10 to the negative 6.2. So second function, 10 to the negative 6.2. And I get 6.3 times 10 to the negative 7. And this, of course, is my Ka. Make this 1. So my Ka of 2. And, of course, this Ka is for the bicarbonate ion. I'm sorry, for the carbonic acid, H2CO3. And generally speaking, even though we were looking at this from the base perspective, we just solved for the Kas of the acid. Okay, you notice that this one, 10 to the negative 7, is about 1,000 times more acidic. We would say the bicarb ion, I'm sorry, the hydrogen carbonate or the carbonic acid is about 1,000 times more acidic than the bicarb. So it's a very important point, in a diprotic acid, H2CO3, we really look at the first Ka, or the Ka of the strongest or the largest Ka first. The second one we don't usually consider. These are both weak to begin with. But you can clearly see that it's 1,000 order difference here. You know, 9.8 to 6.2, that's about an order of, what, 3, right? 3 pHs log 10, there's 1,000 times difference in its buffering capacity. Okay, and we made two buffers. Here you had a CO3H2O buffer, okay, which is best buffered around 9.8, all right, because that's where the pKa equals the pH. And we made another buffer where we had what? We had a bicarb to bicarbonate ion, and this is the buffer in our blood. And now its maximum buffer solution is 6.2. Our body actually buffers at about 7.4, so we're on the more basic end. And the general rule of thumb of buffers is that you should be around plus or minus 1 or 10 times difference if you think about orders of magnitude around your max buffer pH. And it's max buffer because you can buffer from both directions. Okay, so now we're almost done. Now we have our Kas. To validate this position, all we have to do, okay, all we have to do, all right, is, I'm going to validate this position here. All we have to do is take our K, do an equilibrium problem. We know CO3, negative 2, is going to become HCl3. We had a certain number of, concentration is 0.49, and I got that from this. And this is 0. So these are my initial. Here's my ice table. Missing your ice table. Here it is. This is going to be minus X. This is going to be plus X. Okay, let's get rid of some stuff out of the way here. And of course, this is 0.49 minus X. And this is going to be X. Remember, this X I can approximate away because the KB is so small. Okay, this is not going to be markedly different than 0.49. It's going to be a tiny number compared to this, so I don't need that. So the KB, which we're going to get in a second, is equal to the expression here of the reaction, which is going to be, well, it's CO3. So we're going to have X, okay, KB equals X, so we have, and let me just add in some components that I forgot here. CO3 plus water is going to make H2, the bicarbonate ion plus the hydroxide. So this is going to be a 0 as well, and this is going to be a plus X as well. And just getting stuff out of the way here. This will be an X. So what you're going to have is X squared, okay, over 0.49 equals my KB, and you solve for your X. Okay. Now, how would I do that? Let me just get some stuff out of the way. That's very simple. How did I set that up? Well, I know that my law of mass action, or my equilibrium expression, is going to be HCl3 negative times my hydroxide all over my CO3 negative. So I just plug that in. XX, this is 0.49 minus X. I got rid of the X, so we approximated that away. And that's equal to your KB. Now, what is our KB? Well, our Ka is 1.58, and you should know that Ka times Kb equals Kw. Okay, so I should be able to solve for my Kb, so 10 to the negative 14, which is my Kw, dividing by my Ka, which is 1.58 times 10 to the negative 10. Let's do that. Second function, e to the negative 14 divided by 1.58. Second function, negative 10. And I get a Kb equal to 3.99 times 10 to the negative 20. Okay? And make sure I did that right. Okay, no, I did not do that right. So let's make this a little neater. So what I'm doing is I'm taking 10 negative 14 divided by 1 times 1.58, which is the K that we found before, times 10 to the negative 10. Okay, and I get a Kb equal to 6.33 times 10 to the negative 5. That makes a lot more sense to me. So back to this work here. Okay, I'm going to plug that value in. And here we go. Kb is 6.33 times 10 to the negative 5. I'm going to solve for this by multiplying this by 0.49, just doing algebra. And I'm solving by x by doing the square root of that. And let's see what we get. Okay, you put that in your calculator, and x equals 0.0055, let's say 7. And what did we just solve for? We solve for the hydroxide ion concentration. So we'll do negative log of that to get the pOH. Many ways you can do this from here, but I like to do the pOH, so I go negative log. And I get what? And I get a pOH equal to 2.25, and 14 minus that is I get a pH of 11.75. Okay? Yeah, a lot of work, but if you understood a lot what I did here, man, you are such ahead of the ball game. So I get a pH 11. What did I get here? 7.5, and that somewhat validates what I think this starting value would have been. Okay, if I follow this line, it's 11 or both. But so you get the idea that we definitely evaluated that. So certainly go back and slow this down and see what I did here. But this is what I expect you to understand. Have a good day.